All right, let's jump right into this explainer and look at how we can use math, basically as a language, to translate real-world scenarios into super efficient codes. I mean, people often think of math as just abstract numbers floating on a page, right? Or maybe something stuck in an academic textbook. But it's honestly so much more than that. It's actually a highly structured way to describe the whole universe around us. It's kind of like the ultimate compression algorithm for reality. And today, we're zeroing in on a very specific, totally powerful type of mathematical translation, the linear polynomial.
So, think about it. How do we take the complete chaos of the real world, like, say, draining water tanks or wildly fluctuating cell phone bills, and translate all that noise into a perfectly straight line? Well, to get to that final visual payoff, we first have to figure out how the messy, constantly changing real world can be modeled so cleanly. Because whether you're pricing out a huge expanding landscaping project, tracking your mobile data month over month, or measuring the dropping water level in a massive industrial tank, these totally different events actually share a hidden, highly predictable rhythm. And by the end of this explainer, you're going to see exactly how we capture that rhythm. Section 1. The Anatomy of Math. Before we start building complex models, we really need to understand the basic building blocks. So we're going to start at the microscopic level to build up our vocabulary. Picture a quick run to the store. Say a guy named Raju goes in and sees these sealed boxes of supplies. Let's say the red boxes have exactly 4 pens each, and the blue boxes have 5 pencils each. If he buys an unknown number of red boxes, we'll just call that unknown quantity X, and an unknown number of blue boxes, let's call that Y. And then the shopkeeper just tosses in 3 free pens on top as a bonus. How do we actually write that down efficiently? We definitely don't want to write out a whole paragraph explaining the situation. Instead, we can compress that entire messy transaction into one simple, elegant expression: 4x plus 5y plus 3. Now this is where it gets cool. When we parse the anatomy of that expression, we're literally looking at the underlying syntax of reality. The separate pieces connected by the plus signs, the 4x, the 5y, and the 3, those are called the terms. The letters x and y act as placeholders for changing realities, so those are our variables. The numbers stuck directly to those letters, the 4 and the 5, those are the coefficients, and they dictate how heavily those variables weigh in the equation. And then there's that standalone 3, which never changes no matter how many boxes Raju decides to buy. That is our constant. This syntax just gives us a standardized way to talk about moving parts.
Let's scale this up a bit to a bigger, more demanding problem, like modeling a landscape project. If we have a rectangular garden with a length L and a width W, and we want to cost out different fencing and seeds, we just apply those exact same anatomical rules. Let's say wire fencing along the lengths is 100 rupees a meter, wooden fencing along the widths is 80 rupees a meter, and planting seeds across the inside area is 50 rupees a square meter. The total cost naturally scales into the expression 200L plus 160W plus 50LW. It definitely looks more robust, sure, but fundamentally, it's just variables, coefficients, and terms working together to perfectly scale a real-world space to any dimension.
Section 2. Defining the linear polynomial. Let's zoom out a bit and figure out what makes the specific polynomials we're studying today so special. Polynomials are basically grouped by their degree, which is just the highest power or exponent of the variable in the expression. If you've got an expression with a squared term, it forms this swooping parabolic quadratic curve. If the highest power is a 3, it builds a more twisty cubic wave. But today, our laser focus is purely on the degree 1 category, the linear polynomial. Think something like 3z plus 7. You'll notice there are no visible exponents there. It's a pure unbending relationship. That lack of higher powers is exactly what keeps everything straight, predictable, and incredibly reliable.
To keep things super clean and really lock in our understanding, we're going to restrict our focus even further to linear polynomials with just one variable, also known as univariate polynomials. A perfect example is finding the perimeter of a square. If a square has a side length of x, the perimeter is simply 4x. One variable, degree of 1. It is simple, elegant, and basically the absolute baseline for modeling predictable change.
Section 3. Modeling growth and decay. Now that we have our tools and definitions, let's zoom out further and watch these expressions actually move in the real world.
Instead of looking at these expressions as static puzzles just sitting on a page, try to see them as input-output machines. Think of a linear expression like a highly deterministic factory machine. You feed a number into the variable, that's your input, the machine does its multiplication and addition, and it hands you back a perfectly reliable result, your output. Because the machine is completely deterministic, if you put the same input in, you will always get the same output. By changing the variable, you predictably change your result.
When our machine runs over equal intervals, let's say over equal increments of time, it generally does one of two things. It either models linear growth, where the output goes up by a fixed amount every single time, or it models linear decay, where the output goes down by a fixed amount. The absolute magic word here is constant. The rate of change never wavers, it never speeds up, and it never slows down.
Let's ground this with a real example of a draining water tank. At month 0, the water height is exactly 3 meters. At month 1, it's 2.5. At month 2, it's exactly 2 meters flat. Because the height drops by exactly 0.5 meters every single month, without fail, this is a literal textbook example of linear decay. If we asked you what the height would be at month 5, you'd easily predict it would be 0.5 meters. That constant difference is what makes it undeniably linear.
Final section, visualizing linear relationships. Let's move to our ultimate visual payoff and zoom all the way out to see the big geometric picture.
So the crucial point is that any linear pattern, whether it's our draining water tank, a steadily growing pattern of tiles on a floor, or a cell phone bill predictably jumping up by a fixed rate per gigabyte, can be translated and drawn on a graph as a perfectly straight line. And the universal code, the master blueprint to draw that line, is y equals ax plus b. This single equation governs countless everyday phenomena. Let's break down exactly what a and b actually do visually to create this line.
The a in our equation, that represents the slope of the line. The slope tells us the exact angle or steepness of our straight line. It is the geometric representation of the rate of change we were just talking about. A positive slope visually shows growth, with the line pointing upward as it moves from left to right. A negative slope shows decay, with the line aggressively pointing downward.
And b, our constant term from the very beginning of our anatomy lesson, is the y-intercept. This tells us exactly where our straight line cuts across the vertical y-axis and starts its journey. It basically represents your initial conditions. For example, if your master equation is y equals x plus 3, that line slices through the y-axis exactly at the number 3. It's ground zero, your absolute starting point when the input variable is at 0, before any growth or decay has even had a chance to begin.
Okay, let's take a quick breath and recap our journey. We started with the microscopic parts of an expression, terms, variables, coefficients, and constants. We then built them into degree 1 polynomial machines. We watched them process real-world scenarios through linear growth and decay, recognizing their incredibly reliable, constant rate of change. And finally, we translated them into their ultimate visual form, straight lines on a graph ruled by the equation y equals ax plus b.
I'm going to leave you with this final visual puzzle to ponder. We know that a controls the angle and b controls the starting point. If you have a set of linear equations where the starting point, the y-intercept b, keeps shifting up or down, but our angle of growth, the slope a, stays absolutely identical, what famous geometric relationship do we create? Think about it. Lines with the exact same steepness that start at different heights will never ever touch. Yup, they are parallel lines. Mathematics really is a beautifully consistent language. Thanks for joining me on this explainer, and definitely keep looking for those hidden linear patterns in the world around you.